All right, today we're jumping headfirst into something that sounds, well, completely bonkers. We're talking about wave optics, a world where the stuff you think you know about, reality, kind of gets thrown out the window.
So let's just get right to it. Here's the question that just breaks your brain a little bit. How can you add light to light and get darkness? I mean, think about it. That shouldn't be possible, right? If you shine one flashlight on a wall, it's bright. You add a second flashlight, it gets brighter. But I'm telling you, in physics, you can add light to light and get nothing. Pure, absolute darkness. So, what on earth is going on?
And this really gets at the heart of why this feels so wrong. In our day-to-day lives, things just add up, right? If you throw a tomato at a wall, splot, one tomato. You throw another one, splot, two tomatoes. It's simple. Matter plus more matter equals, well, more matter. But with light, that rulebook goes out the window. This whole contradiction, this is the key to understanding everything we're going to talk about today.
All right, let's dive in. We're going to tackle this strange contradiction head on. And to do that, you and I, we need to completely change how we think about light.
And here's the secret. It's actually a pretty simple idea, but it changes everything. The whole mystery just dissolves. All we have to do is stop thinking of light as a little thing, like a tiny bullet or that tomato we were talking about. We have to stop thinking of it as a particle and start thinking of it as a wave. Okay, so if light is a wave, that brings up some new ideas. And the first big one we need to wrap our heads around is something called a wavefront. So, what in the world is a wavefront? Imagine you drop a pebble into a still pond. You see those ripples moving out, right? A wavefront is like taking a snapshot and drawing a line connecting the very top crest of one of those ripples. It's an imaginary surface that links up all the points on a wave that are vibrating in the exact same way at the exact same time. All the peaks are connected, all the troughs are connected, you get the idea.
Now, the cool thing is, the shape of this wavefront totally depends on what's making the light. So, if you've got a super tiny point of light, think of a single distant star or a little LED on your computer. The wavefronts it sends out are perfect spheres. They just expand outwards in every direction, kind of like a bubble getting bigger and bigger.
Okay, what if the source isn't a tiny dot? What if it's a line, like one of those old-school fluorescent tube lights or a glowing wire? Well, in that case, the light still expands outwards, but instead of spheres, you get these perfect cylinders growing out from that line.
And then there's the last type. Imagine that source is really, really far away. The best example is the sun. It's sending out these massive spherical waves, right? But they've traveled so far and gotten so huge that by the time they get all the way here to Earth, the little section we experience looks totally flat. We call these plane wavefronts.
So, we've got these shapes, spheres, cylinders, planes. But that doesn't really explain how the wave actually moves from one spot to the next. For that, we turn to this absolute genius physicist, Christian Huygens, who came up with a principle that is just so elegant.
Now, Huygens' principle sounds super intimidating, but trust me, it's not. You can break it down into 3 simple steps. Step 1, take any wavefront. Step 2, imagine that every single point on that line is its own tiny source, sending out a new little ripple, which we call a wavelet. And step 3, the new wavefront is just the outer edge that all of those little wavelets create together. It's like a constant, beautiful ripple effect creating the next ripple.
And that is the big idea. You really have to let that sink in. A wave isn't just one thing moving forward. It's this infinite collection of tiny new sources all working together to build the next wave. This idea, this is what's going to unlock our whole light plus light equals darkness mystery. Okay, we've got wavefronts, we've got Huygens' principle, we have everything we need. Now we can finally go back and solve that riddle from the beginning. Let's talk about what happens when these waves crash into each other. Let's talk about interference.
And boom, here's the answer. It's actually super simple. When two light waves meet, there are only 2 possibilities. Possibility 1, the waves arrive perfectly in sync, or in phase. The peak, the crest of one wave lines up perfectly with the crest of the other. When that happens, they add together and you get a bigger, brighter wave. That's called constructive interference. Light plus light equals more light. Totally makes sense. But possibility 2, the waves arrive totally out of sync, out of phase. The crest of one wave lines up perfectly with the lowest point, the trough, of the other. And what happens then? They completely, totally cancel each other out. And that is destructive interference. That is how light plus light equals darkness.
At the end of the day, it's just math. It all comes down to the amplitude of the waves, basically how tall they are. When they interfere constructively, you just add their heights together. A1 plus A2. Simple. But when they interfere destructively, you subtract one from the other. A1 minus A2.
So what happens if two waves with the exact same height, the same amplitude, meet up perfectly out of phase? Well, you get 1 minus 1. You get 0. Nothing. Total, perfect cancellation. At that one specific point in space, there is no light. It's gone. It's as if it was never even there.
And what's so cool is that this whole wave idea isn't just about our light plus light equals darkness trick. It explains a bunch of other weird things that light does. Things you've definitely seen before, probably without even thinking about it.
For example, let's talk about diffraction. This is just a fancy word for the fact that light tends to bend a little bit when it goes around a corner or squeezes through a tiny opening. Now think about our tomato particle. It would either hit the wall and stop or go straight through the opening. But a wave bends.
And why does it bend? You already know the answer. It's Huygens' principle again. As that wavefront hits the edge of something, those little points right on the edge become new sources of light, sending their own little wavelets out in all directions, including into the area that's supposed to be a shadow. And this is why shadows are never perfectly razor sharp. There's always that tiny bit of a fuzzy edge. That fuzziness, that's diffraction.
So the big takeaway here is that thinking of light as a wave isn't just some weird thought experiment. It's an incredible tool that explains so many things we see in the real world. It explains the shimmering colors you see on a soap bubble or an oil slick. And yeah, it explains why you can never get a perfectly sharp shadow. It's like we've cracked the code behind all these beautiful and strange patterns that light makes all around us.
But this leaves us with one last massive question, doesn't it? I mean, we get it. A sound wave is air that's waving. An ocean wave is water that's waving. So, if light is a wave, what exactly is it that's doing the waving? What is the stuff that light is a ripple in? Well, that's a story for another time. Thanks for joining The Explainer.